Hello, everyone. I'm Anna Kia Santos, and I'm a postdoc at the University of Nottingham in the UK. And it's really nice to be here today to tell you, to introduce you the Omega survey. Omega stands for the OSIRIS mapping of emission-line galaxies in A901-2. And this is a multi-cluster system at redshift 0.17. And this work is done mainly in collaboration with the PhD student Bruno Rodriguez del Pino. And the PI of the survey is Alfonso Aragon Salamanca, and we work also in very close collaboration with Stephen Bamford and Megan Gray. So our goals are to study the environmental dependence of star formation and AGN activity using the optical lines H-alpha and nitrogen-2. What's special about these lines? Well, regarding star formation, the H-alpha flux is a very good star formation rate indicator. And we want to do an AGN census. And we're using the one diagram. That is a diagram that is a simplified version of the BPT. That in the x-axis, we have the line ratio of nitrogen-2 over H-alpha. And in the y-axis, the equivalent width of H-alpha. And we don't need the O3 over H-beta line ratio to pick out AGN from star-forming galaxies. So we want to measure star formation rates down to 0.1 solar masses per year and understand the role of obscured and unobscured star formation as we have UV and infrared measurements. And most importantly, we want to understand the concentration of the star formation regions by doing resolved star formation studies with a resolution down to 3 kiloparsecs in 1 arcsecond C. And regarding the AGN activity, we want to understand the role of low luminosity AGN with no X-ray emission. So we're using the tunable filter observations from one of the several inventions of humanity named OSIRIS. When I heard I was going to work in this survey, I went down to the British Museum in London and I found a statue of Osiris, the Egyptian god of afterlife, the underworld, and the dead. But it also happens to be the name of 4 or more astronomical instruments, and I'm sure you're well aware of that. And the one we're using, is the one on the Gran Tecan in the Canary Islands. Omega is an ESO large program of 90 hours at the Gran Tecan, which is a 10.4 meter telescope, and it's completed as of February this year. And we've also finished reducing the data. And we're using then the tunable filter mode of OSIRIS to gather narrowband images. So this is the Combo 17 image of this multi-cluster structure. It's 0.5 by 0.5 degrees on the sky, and you can see the different structures outlined. And that's about the size of the full moon in the sky. And we're placing OSIRIS pointings all over the cluster. There are 20 pointings, and they have a diameter of 8 arc minutes each. And for the remainder of the talk, I'm going to concentrate on the green and the red pointings that were the first pointings we got data for, and were the ones we used as kind of guinea pigs to test our data reduction techniques and analysis. And there also happens to be the densest. And just to remind you that this region has been extensively studied by a variety of telescopes and instruments, including the HST, and there's also XM Newton and Spitzer. So how does a tunable filter work? Long story short, you have 2 plates called an etalon, and by changing the distances between these 2 plates, you can tune the wavelength you're going to get. And one of the complications you have is that the wavelength varies across the field of view according to this equation. And here's a cartoon illustrating this. So from the center to the outskirts, we have a maximum variation of 80 angstroms. And to optically deblend these two lines, we use a tunable filter full width of maximum bandwidth of 14 angstroms. And we have a spacing between the successive wavelengths of 7 angstroms each. So here's the redshift distribution of the 300 brightest cluster galaxies from 2DF data, so proper spectra. And for the main survey on the top panel, we use 16 wavelength settings. And for the green and the red ones that I'm going to concentrate now, we use 14 and 12. And here's an illustration of how the observations are done for a given galaxy. So, for instance, for field 22, we have 3 observing blocks, and we separate these observing blocks in 4 different wavelength settings, and they're spaced 7 by 7 angstroms each. And we have 3 dithered images at each of these wavelength settings. And each image consists of 200 seconds. So in total, we would have for this field, for each galaxy, 36 images. So I don't want to bore you with data reduction techniques, but this is how a raw image of OSIRIS looks like. You have these rings, and these are sky rings, skylines, and all the data that we have outside this radius we don't use because there's wavelength interference patterns. And after it goes through the pipeline, we get a nice looking image like this, and we're ready to do photometry. So we do aperture photometry by using a central aperture in red and a total aperture which encompasses the whole extent of the galaxy. And this is we've got we used the measurements from HST and Combo 17, where they've ran GalFit on it. So we're ready. So once we do photometry in all of the images, we're ready to build a spectrum. And this is what it looks like for the central aperture and for the total aperture, and you can see H alpha and the 2 nitrogens. And this is a movie for one of these galaxies, and it's the one here where we have the HST postage stamp, where you can see while you scan the wavelength, the H alpha popping in, and the nitrogen 2 as well. So now we're ready to do the spectral modeling, and when we give this talk, we like to give examples, to use myself and the PhD student that work with me, Bruno, because he's the tallest and I'm the shortest person at the department. So, so in this configuration, we are a star-forming galaxy, and if I were to jump on a table, we would be at AGN. Anyway, Bruno, besides being H alpha, he's a great PhD student. He's on the job market, and he's responsible for the spectral modeling part of this work. So we use 3 Gaussians to model our data plus continuum, and a total of 6 parameters. And we say that the flux of the big nitrogen has to be 3.06 times the flux of the small one. And the parameter space is explored by using MCMC techniques. And now finally to the results, and it's only for the first 2 fields. So here are some examples of our detections. We divided the sample, we made 2 samples, one where we have securely detected H alpha, and another one where we have both H alpha and nitrogen 2, because the wavelength varies across the field of view, and sometimes in this single field that we're looking at, we don't have the complete coverage, but we will have in subsequent fields. So in total, we have 142 objects with H alpha detection and 79 with both H alpha and nitrogen 2. And here's our one diagram for our both H-alpha nitrogen 2 detections. We have 79 objects, and we can securely say that 23 look like star-forming galaxies, and 10 look like AGN. And this is the distribution on the sky of our detections. And the AGN and the star-forming galaxies tend to avoid the very central regions. And regarding their morphologies, there's a hint that the star-forming galaxies tend to be of later type than the AGN that are of earlier type, although they're mixed up in SB, SC types. And regarding the mass and the magnitudes, the brightness, the AGN tend to be more massive and brighter than the star-forming galaxies. And when we look at the star formation versus stellar mass plane, we compare with the Whittaker 2012 relation for this redshift, we find a suppression of star formation. And we've also checked the luminosity, the H-alpha luminosity function, and compared it, our both uncorrected and corrected for completeness, both with the gamma at this redshift range and with the Balog one for the relaxed cluster 16 of 9. And it's in between. So this is the end. Thank you for listening. I've showed you the analysis of 2 out of the 20 fields of this survey. There's much more to come. We're working on the full AGN sensors and integrated star formation properties of the 20 fields. And most importantly, we're developing the machinery to study the sizes of the star formation regions from the H-alpha maps and its dependence on environment. So stay tuned for our first paper that's about to be submitted, and we have one more in the pipeline regarding the full census. Thank you.
Thanks. Questions? David?
How do you account for the H-alpha absorption? What procedures do you take?
So he allows, in the spectral modeling, he allows a 5 angstrom. I can tell you later. I cannot remember out of the top of my head the exact number, but it's allowed in the modeling.
Okay. Anything else? Can you give us any hints or previews on what you're finding with the integrated star formation properties?
We haven't. We are still really in the beginning of the development.
Okay. All right. Well, thanks very much.